In this video, we're going to take a look at an easy example of uniformly accelerated motion. And our first objective is to just familiarize you with the 4 steps required for solving these problems. And the secondary objective is to show you that what equation you use as your starting point is irrelevant. All of our equations of motion come from the same place, and so any one of those equations become a valid starting point. The only difference between the equations is that some of them are less efficient at solving the problem than others, meaning it's going to require more algebraic steps in order to get to the final answer. So we're going to do this problem 3 times. The first time we do it, it's going to be the more direct route, and then the other 2 attempts will be less direct. Okay, so in step 1, all we're going to do is draw a picture of what's going on, and that's going to provide us just a visual, and that's going to be very important, very helpful in most of the problems that we do. So we have a car that accelerates over a distance of 300 meters, and so you would just say that you've got 300 meters between these 2 points. At this point, the initial velocity is equal to 0. We would also say that this is time equal to 0, so t naught. And then down here we have v final is an unknown quantity. That's what we're looking for, so we're going to put a box there in that space. I'll explain all this in a minute. And the time to reach this location is 7.0 seconds. Alright, so that's step 1. We've identified everything we at least think up to this point. Now, step 2, we're going to list out all of the variables that we use with kinematics problems. And the primary reason for doing this is to make sure that we don't look over something that we might otherwise miss because the information is implied. So I'm just going to start by writing out x final, x initial, v initial, v final, a, and t. And because this is one part motion, one object, I'm not going to worry about putting any additional subscripts on my variables. Alright, so the final position and the initial position together form the displacement. So I'm going to label that as d and just write it as 300 meters. Now, if you wanted to, you could have made the 300 meters go to the left, and that would have been a negative 300. The choice is yours, but way more often than not, you're just going to assume that it goes to the right unless otherwise indicated. V initial, we're told, is 0. V final is what we're looking for. The acceleration is an unknown quantity, so I use a question mark. And the time interval is 7.0 seconds. Now, a little bit about how I notate my variables. Of course, if I have a value, I put that value beside the equal sign. But instead of using question marks for everything that's unknown or I'm trying to find, I use a box for what I'm trying to find, and that's just a visual reminder to not accidentally eliminate that variable from my problem through algebraic substitutions. I've done it in the past. You'll end up doing it. Everybody does it, but having a box instead of a question mark is just a nice reminder of that. Anything labeled with a question mark is unknown. It's not explicitly stated in the problem, nor is it implied through the wording of the problem or the context of the problem. For example, if you drop a rock, the implication is that the rock has an acceleration of 10 meters per second squared downwards. And we'll talk about that whenever we get into free fall. So the question mark is, I don't know what it is explicitly or implicitly. I may have to do something else to take care of that particular variable. Now, for step 3, we're going to take a look at the equation sheet. And you can see here on the equation sheet that we're solving a problem, and that means we're going to be looking primarily at these 3 equations here to do the problem solving. And it's all about interactions. An interaction is going to create a change. In this case, our motion is changing, the velocity is changing. These are the 3 equations that we go to whenever we have a problem to solve with kinematics. And we've got first the position function, then we have the acceleration independent equation of motion, and then finally we have the time independent equation of motion. Now, when you select your equation, obviously you're going to be looking at the variables that you have and see which equation best matches the variables that you have. But sometimes there's more than one option available to you, and that is where intuition is going to be important. That experience piece, that's what I can't give you. You have to figure that out for yourself. Which one is going to be the better equation? Which one lets me get through the problem the quickest? So in this particular example, we know the displacement. All 3 of these equations have the displacement. We know the initial velocity, and again, all 3 of the equations have the initial velocity, so we can't make any distinctions yet. The final velocity is what we're looking for. So right away, what we see is the position function would be a poor choice, because it doesn't give us what it is that we're actually looking for. And not only that, it's introducing an unknown variable, the acceleration. Again, that's something we don't know. So choosing the position function would be silly. Finally, let's see here, we have the acceleration, or we don't know what the acceleration is. So that is going to eliminate the position function once again, but it's also going to eliminate the time-independent equation of motion. So it would appear that the only equation that makes any sense is the acceleration-independent equation of motion. So let's use that as our starting point. We have d is equal to 1/2 times v initial plus v final times t. Now, in this step, we're going to solve this for what we want. Now, what we're looking for is the final velocity, and the initial velocity is 0, and actually it's usually quite helpful to, early on in the process, eliminate those things that are 0. And so the initial velocity is 0, that whole term is going to go away. So that's going to give us 2d over t is equal to v final. Okay, so at this point we're going to go through our checklist. And our checklist is basically, do we have that variable? Do we know what that value is? And anything that's an unknown value, we have to find that value somewhere else. And you'll see that in a significant way with our next attempt. So 2 is a constant. D, that's been given. It's 300 meters, so I'm going to check that off. T has been given. That's 7 seconds. I'm going to check that off. So this means now I can actually solve the problem. So in step 4, we're going to solve the problem, and we get v final is equal to 2 times 300 divided by 7. And that will be 85.7 meters per second. Okay, so like I said, this is just an easy example. Now let's go ahead and look at some alternate solutions to this problem. So we'll call this alternate solution 1. All right, let's go back to our equation sheet and see what equations we have to use. You can see that we've already used the acceleration-independent equation of motion. That was the most efficient way of solving the problem. You could see that it was very little work. It was plug and chug, nothing going on. Our next attempt, our next easiest attempt, or maybe you might say it's the increasingly more difficult attempt, is going to be the time-independent equation of motion. So let's go ahead and try solving this problem using the time-independent equation of motion. Now the time-independent equation of motion is v final squared is equal to v initial squared plus 2ad. And again, we can eliminate those terms that we know go to 0. So v initial was 0, that all goes away. And that's going to leave us with v final squared is equal to 2ad. Going through our checklist, we have this solved for v final. I'm leaving it squared for now just for simplicity, but it's already solved for v final. We do not have a, so we've got to find that. And d is a quantity which has been given. So let's go ahead and find the acceleration. Now the way we do that is we go back to our equation sheet and we look for another equation that we have not used on this attempt, and we look for that equation to have the acceleration in it. Now typically we're not going to look at the law and theorem column for this. We're going to go to our definitions. We want to redefine the acceleration in terms of the variables that we know. So what we do is we just look to see what we have here. And there's only one equation with acceleration in it, and that's going to be the definition of acceleration, or delta v over t. So off to the side, I'm going to do this. To get the acceleration, I'm going to write a is equal to delta v over t, or a is equal to v final minus v initial over t. We know that v initial was 0, and so a is equal to v final over t. So we'll rewrite with the new substitution. V final squared is equal to 2 times the quantity v final over t times d. All right, now notice that this v final cancels with one of these v finals, leaving us with v final is equal to 2d over t. And that's exactly the same thing we had in our first attempt right here. V final was equal to 2d over t. So we did that one correctly. All right, let's take a look at alternate solution 2. Okay, for alternate solution 2, we're going to look at the last of our equations, which is the position function. Now, you can see that this equation makes absolutely no sense at all for the simple fact that it does not have what we were looking for, which means we would never use this equation according to the strategies that I'm teaching you, because the whole purpose in step 3 when it comes to selecting an equation is to give yourself an anchor point. You see, my students in the past, and they've always struggled with knowing what to do with their information. Where do you start a problem? I've seen them do it time and again over the years, where they calculate everything you could possibly calculate, but don't know how to put it together to get a final answer. So the obvious choice is to make sure you select an equation which has what you're looking for, which in this case is v final, and then you work that equation to get what you want. You just got to fill in the blanks. Literally, you have to fill in the blanks. So this problem is going to be a little less obvious because we don't even have v final in it to begin with. So I'm going to do alternate solution 2 simply to show you that it does not matter what equation you start with. If you're careful, it will still get you what it is that you're looking for. So in this particular problem, we have to find a way to introduce v final into the equation. So let's go back to our equation sheet and see what options we have. Now, we're using the position function, so we can forget about looking at that right now. And if we wanted to, let's see here, we could use the acceleration independent equation because right here is v final. We could also try the time independent equation of motion because here's v final once again. And we could also try the definition of acceleration. That will introduce v final as well. Any one of those three equations turn into a valid next step. That doesn't mean it's the most efficient step or the most efficient equation to use, but it's a valid next step, any one of those three. So in this case, we know what D is. If we go through our checklist, we know what D is. We know that V initial goes to 0, where we don't know what the acceleration is, and we know what T is. Substitute out for the acceleration, and the acceleration we'll do like we did before. We'll say that it is V final minus V initial over T, where V initial was 0, so that means A is just equal to V final over T. So we get D is equal to 1/2 times V final over T times T squared. We can eliminate this T with one of those T's. And now solving for V final, we're going to get V final is equal to 2D over T. And you can see that that's the same answer that we got with alternate solution 1 and the real solution that we started off with in the first place. So that's the method in a nutshell. You just got to pick a starting point and work the problem. Let the problem tell you what to do next. And you know what to do next based on the checklist. As you check off those things that you know and you highlight those things that you don't know, it's those things that you don't know that you're going to look for. I would recommend following my my lead with anytime you have an unknown variable that you just draw an arrow off to the side and you show any work that you do to come up with that unknown variable, and then you substitute it back in the next step. This is very important for you being able to track your work and the changes as you go throughout a problem, because it gives you the ability to very quickly find something that you could do differently that might actually make a difference in the problem. The other thing that I want to encourage you with is to try multiple solutions. There will be times throughout the year where I will ask you to do that. You'll come up with an answer using one solution, and then I'm going to tell you to find another one. And that might mean that you're using a different kinematics equation as a starting point. It might mean that you're changing concepts completely. And what I mean by that is some problems you can solve using work and energy. Some problems we can also solve using impulse and momentum. And which of those perspectives we use doesn't really matter. And so to help you see those connections better, I'll ask you to do those things. In the next video, we're going to take a look at a moderate example, something that's moderately difficult.